Instead of answering, the teacher threw him out of the class. That boy's name was Albert Einstein. Einstein left the class, but his question stayed with him. What would the world look like if you could run at the speed of light? It may seem like a childish question, but it would go on to challenge Newton's gravitational theory, revolutionize physics, and give birth to Einstein's groundbreaking theory of relativity. But how did Einstein transform such a simple question into a revolutionary idea? What gaps did he see in Newton's theories that others missed for 200 years? How did he create a new foundation for physics? And more importantly, can we learn to think like Einstein? In today's video, we'll explore the journey of Einstein's ideas, how he questioned the world around him, and how his unique approach reshaped our understanding of the universe. Einstein and Newton's theory. Many believe Einstein's theory of relativity is directly tied to Newton's theory of gravity, but that's not entirely true. In fact, Einstein's ideas marked a significant departure. Newton's key theories covered three areas. 1. Gravity. 2. Bodies with mass attract each other. 2. Particle theory of light. Light travels as small particles, or packets, of energy. 3. Relativity. The speed of an object depends on the observer's frame of reference. At first glance, these theories seemed unrelated, yet they would eventually intertwine to form Einstein's revolutionary ideas. The wave-particle debate. In 1678, Dutch physicist Christian Huygens challenged Newton's particle theory of light, proposing instead that light traveled as a wave. Without experimental evidence, Huygens' idea was dismissed for over a century. Then, in 1801, Thomas Young's famous double-slit experiment demonstrated that light behaved like a wave, creating interference patterns. This finding contradicted Newton's particle theory and proved light's wave-like nature. But this discovery introduced a new question. If light is a wave, what medium does it travel through in the vacuum of space? Scientists hypothesized the existence of a medium called the luminiferous ether to explain this. But when Albert Michelson and Edward Morley conducted their famous experiment in 1887, they found no evidence for such a medium. They also discovered that the speed of light remained constant in all directions. Einstein's thought experiment. Einstein pondered these findings. According to Newton, speeds should add up. If you travel at one speed and encounter another object moving towards you, their speeds combine. But if light's speed is constant, this principle doesn't apply. Einstein imagined a train traveling at the speed of light. If light flashed from both ends of the train, a person on the platform would see the flashes simultaneously. However, a person inside the train would perceive the light from one end arriving first, as the train's motion affects the light's travel distance. This thought experiment led Einstein to a radical conclusion. Time is not absolute. Instead, time itself stretches or contracts depending on the observer's frame of reference. This formed the foundation of his special theory of relativity in 1905. From special to general relativity. While special relativity explained how time and space behave at high speeds, it didn't address gravity. Einstein spent the next decade refining his ideas, ultimately developing the general theory of relativity in 1915. Einstein proposed that massive objects like planets and stars bend the fabric of space-time, creating pits that cause other objects to move as if pulled by gravity. This curvature also affects light, causing it to bend when passing near massive objects. Einstein's predictions were confirmed in 1919 when British physicist Arthur Eddington observed light bending around the Sun during a solar eclipse. This experimental proof cemented Einstein's place in history. Einstein's legacy. Einstein didn't discard Newton's ideas. He built upon them, identifying gaps and extending their applications. Similarly, while Einstein's theories explain much about the universe, they aren't complete. Questions like what happened before the Big Bang or what occurs inside black holes remain unanswered. The next groundbreaking theory